Inference for a relationship. When we talk about relationship, there should be two variables. Recall the role type classification C to C, categorical to categorical, C to Q, categorical to quantitative, Q to C, quantitative to categorical, and Q to Q, quantitative to quantitative. In this case, the role will be either explanatory or response variable, and the type will be either categorical or quantitative variables. For inferential for relationship, we will first consider the case C to Q, where the explanatory variable is categorical and the response variable is quantitative. Let's consider one specific example. Suppose we want to know if there is a relationship between graduation level and income. Graduation level is a categorical variable because we can group graduation level into many groups. No high school diploma, high school diploma, some college, bachelor degree, or master degrees, or PhD degree, and so on. And within each of these groups, we will measure the average income. And so we might measure the income for no high school groups, and the average income of this group is labeled mu1, the mean of the first group, if you will. For high school diploma group, we measure the income and we report this at mu2, and so on. mu3, mu4, mu5, mu6. Remember that we use mu here for the parameters for the population. And we would compare these means to infer on the relationship. In this sense, if we call the explanatory variable x and the response variable y, then we want to know if there is a relationship between x and y. Each of these subgroups is considered as the subpopulation, subpopulation 1, subpopulation 2, subpopulation 3, subpopulation 4, and so on. We will first consider the case where we obtain independent groups, meaning we will have subpopulation 1, subpopulation 2, subpopulation 3, and so on. And these are independent, meaning we pool them, we obtain the sample independently, and they do not necessarily have the same sample size. So for example, maybe we'll get 100 to obtain the first sample, and for another sample we will use 120, and we would compute the mean for the first sample x1 bar, compute the mean for the second sample x2 bar. But remember, in inferential statistic, we want to say something about the population, meaning we want to infer something about mu1 and mu2. And this is when we have independent samples. In some cases, we will have to work with what we call matched pair. Matched pair, they are not independent. However, for the sample size, they have to be the same. If the sample size for the first sample is 100, then the sample size for the second sample has to be 100, because for each individual in the first sample, we match it to another individual in the second sample. And so there is a one-to-one correspondence here. For example, husband, wife. Husband 1, wife 1, husband 2, wife 2. We can't mix them up. Or twin 1, twin 2, twin 1, twin 2, and so on. Or it doesn't have to be from individual to another individual. It can be the same individual. For example, for the same individual, this is before and this is after. This is how people behave before they get drunk, and this is how they behave after they get drunk, and so on. To summarize, for the inferential relationship for the case C to Q, we might compare the two means, or we might compare more than two means. We might compare independent samples, or we might compare masked pairs dependent samples.